Okay, so we're going to get started here. Welcome. My name's Martin Hull. I'm the Director of Product Management at Arista Networks. And I get the plug in early. So when you're done here, once you've finished looking around the Seagate booth and you've got all the information you want, take a walk down there. It's about a 5-minute walk and you'll find the Arista booth. So do come check us out and mention my name. I think my bonus depends on how many people I get over there. So today, going to be a short talk on what the impact is of a deep buffer switch on an environment that's built for high performance compute and storage. You know, perfect topic for here at the Supercomputing Show. Every year we attend Supercomputing and we keep talking about the new innovations in networking. And, you know, this photograph was taken of the German Autobahn, right? And when we're building networks, we constantly come up against congestion issues. I just don't want to be the guy that's down here, is taking his life in his hands. But we're building these high performance networks, and really, what we wanted to achieve was this perfect nirvana, right? That the network just gets out of the way. There's no congestion, there's no overflows. And really, what we're dealing with is that as storage gets faster over the generations of technology, storage has the ability to consistently oversubscribe network from both an incast and a surge perspective. So the modern storage is 10 to 100 times faster than what we've been used to in a traditional perspective. The other side of the equation, on the server side, we're increasing the CPU, the compute power. That in turn is leading to a higher and higher density of virtual machines, which in turn is then leading to more network traffic. So we're pushing more traffic onto the network. What that results in is congestion, which I showed in the picture earlier. Too much traffic arriving simultaneously. Congestion is naturally inherent in large networks. It's a pure, simple function of the dynamic traffic, the pattern, the application behavior, and traffic will be bursty. Traffic isn't perfectly distributed over your network. You don't get an even distribution that arrives just when you want it. And the problem that we're dealing with is a synchronization of the behavior of the applications. So that can happen in a storage environment, or it can happen in a Hadoop environment, where all the nodes try to pull traffic at the same time, or they all try to push traffic back onto the network at the same time. So multicast and other bursty traffic is that characteristic. And if we don't have buffering in the network, packets drop. That's okay. We have an IP Ethernet network. Packets are a normal effect, and we just retransmit them. The problem is that the packet that gets dropped isn't calculated, it's not predetermined, and so we get an unfair allocation of bandwidth to some flows and we get more bandwidth to other flows. This results in unpredictability. Applications sometimes run well, sometimes they don't, and you can't necessarily identify what the cause of that is. So let's look at the effect of those drops in a bit more detail. So the consequence of a packet drop is, you know, packets drop if there's no buffer. If the buffer exhausted on a switch, we just discard the traffic. Those drop packets in turn cause retransmission. The retransmission results in throughput suffering, as the actual amount of good traffic I can get through the network is a function of throughput minus bad put, or retransmission. And as the traffic becomes more and more correlated with a Hadoop or a storage environment, that actually leads to a greater probability of a drop. And so at the time that you need the network to perform at its best, it's actually congested, you're going to get drops, applications are going to form. And the randomness of the drops leads to gross unfairness across the flows. Now at Arista we've done a serious amount of work on modeling this. We don't have time today to get into the simulations and testing we've done, but I'm going to show you the results of that. We will be publishing a white paper that details the simulations and the results. So what we're doing is we're calling this the TCPIP bandwidth capture effect. As we all know, TCP uses the ACK, or the acknowledge, to pace the transmission of packets. When there's congestion and when there's insufficient buffer, we just drop the packets. That's okay. But the drop packets then signal to that sender to reduce the amount of transmission that they're sending onto the network. The problem is, which particular flow gets affected by that drop packet is literally a statistical fluke. You can be lucky or you can be unlucky. Lucky flows get more bandwidth because the other flows get out of the way. But unfortunately, those unlucky flows back off and consistently get less and less bandwidth. And some really unlucky flows literally get hardly any bandwidth at all. So this is a simulation we've done for both a shallow buffer and a deep buffer switch. So in purple in the middle, we're showing the deep buffer switch, where on average, every flow gets 200 megabytes, and that gives you perfect fairness across the network. The shallow buffer switch, because we're constantly hitting the congestion, we will get some flows backing off, all the way down to literally some flows getting as little as 12 megabytes of traffic, whereas other flows never get a congestion, never have a packet drop, and will get consistently more. So in a normal enterprise class network, this is okay. Your networks aren't consistently congested, but in a data center network, in a high performance network, congestion is a matter of normal business. So what that means is just at the point where you're loading the network up to its peak, so we have the traffic load increasing here on the bottom axis. So as we're starting to load the network up to 90% load, which would happen at the peak utilization, what happens is some packets are going to get congested, some packets are going to get dropped, and those flows will take longer. If you're running a type of job that relies on all the flows completing before that test or that job is complete, then you're going to get very slow job completion because the retransmissions are happening in the background. What you're going to get is what we call the long tail effect. So the first flows will go through quickly because they're getting any drops, but the other flows will take far, far longer. So we're seeing here a 50-to-1 difference in the performance of a shallow buffer versus a deep buffer at 95% traffic load. And I say your normal network is not going to be running at that, but at the peak times when you most need it, that's what happens. So now I'm going to talk about the Arista 7280, and clearly the point of this is it's a deep buffer switch. It has both 40 gig and 100 gig uplinks, so it's actually the world's first fixed configuration switch with 100 gig uplinks. It works well with the Arista 7500, we'll get onto that later. One of the key characteristics of the 7280 is it has 9 gigabytes of packet memory. It also has large table sizes, large access lists, so you can use it in the most demanding network environments. And of course it has 48 ports of 1 gig and 10 gig. So it's a fixed configuration top of rack switch with a deep buffer architecture. Now inherent to the nature of the switch, it also has what we call a virtual output queue architecture. So when we do get the instantaneous congestion, we get the incast where all the traffic's trying to congest to one single egress port. The virtual output queue architecture means the switch remains non-blocking. In a traditional non-VOQ architecture, one single flow could congest an ingress port. Doesn't happen on the 7280. So just to put that in context of the buffer size, a traditional top of rack switch would have a 9 megabyte buffer. And we're now talking about a 9 gigabytes. So it's 1,000x. So it gives you the capability to build a lossless network optimized for big data, IP storage, high performance compute, or just simply large incast environments. So we take this product at the top of the diagram here in our leaf topology, and we use the Arista 7500E in the spine. The 7500E has been shipping for many years now and uses the same deep buffer architecture as a modular switch. So we have ultra deep buffering at both the leaf and the spine, optimized for the bursty applications, the ones that are most in use in the highest performance networks. And we also enable a number of features because, as I showed earlier, we don't know if the network's going to be congested or if it's running in nirvana. So we have our data analyzer and latency analyzer capabilities to actually monitor buffer utilization. So you can actually tell how much of the buffer is being used and which flows, which applications are actually congesting that network, and maybe you can re-engineer to make sure you get a better load balancing. With the 7280, we give you a choice of either using 40 gig or 100 gigabit as the uplink technologies, and we have a choice of both single mode and multi-node technologies, depending on the size of the network you're trying to build out. Talking about size, this will actually scale to over 12,000 10 gig ports in a simple two-tier leaf spine design, so very scalable. So when we've done this testing, this is an excerpt from a company called DataSift who moved from a shallow buffer switch to a deep buffer switch, and they saw a 7x improvement in their application performance. And if you go onto these links at datasift.com, you'll see that this was the result of their real-world testing, switching out traditional product for deep buffer capabilities. So in summary, what we're doing is we are increasing the performance of your high-performance storage. It's allowing you to build out scalable IP storage networks, get the benefits of fiber channel or InfiniBand-like delivery on an IP standard. The ultra deep buffers in the Arista products are going to guarantee your packet delivery. You can go down as low as 2-to-1 oversubscription, or you increase the oversubscription depending on your requirements. It allows you to scale out the storage nodes as you need without any concern. And we provide the tools within Arista's EOS to pinpoint any network bottleneck, whether it's latency analyzer or it's our telemetry capabilities to do tap aggregation into those networks. So with that, if there are any questions, I'll take them now, or I'll be around for a few minutes, or you can come and see us over at the Arista Networks booth. Thank you.